Brian Malloy here, and today I want to talk about the meaning of a virtual function in a base class. And it's really the key ingredient that empowers polymorphism. So it's important if we want to use polymorphism, and I can't imagine why we wouldn't. So it's important to understand what a virtual function means in order for us to grasp the importance and the meaning and the use of polymorphism. So what I have here, and I apologize, is kind of the canonical inheritance example. And I'm going to revert back also to that vanilla one that I used in the first video. But I just wanted to talk about a virtual function in the context of this canonical example of a shape. People use this all the time. So here I have a base class called shape. And to give it a data attribute, I gave it a name. So every shape has a name. And I'm thinking that we might want to give, if we want to identify what kind of shape it is, we could pass circle or rectangle or square or whatever kind of shape that we have in as part of the data attributes of the base class. So we have some reuse there with the get name, or maybe even a set name if we want. Initialization lists the whole thing. We also have, and more importantly, on line 8, a pure virtual function called area. And what this says is, by virtue of the fact that it's purely virtual, it means that every derived class must implement area. So I provide an implementation for area in circle, and I'm hoping it's appropriate for a circle, pi r squared. I have an implementation for a rectangle, and I can find the area of that by multiplying the width times the height. And those are the only two derived classes I have, and I must provide an implementation as I described in video 1. So what does it mean that these functions are virtual? So I'm focusing now more on the fact that they're virtual rather than pure virtual. Pure virtual means I must provide an implementation in the derived class. What does the virtual part mean? Okay, well, let's come down here to an instantiation of a shape. So what I have here is a pointer to shape, shape star, shape asterisk, whatever you want to call it. And then I have a variable called lowercase shape. And then I have an instantiation of shape. And in this case, it's a circle. So what I want to point out to you is that there's a lot going on down here. There's the type of the variable, shape star. And then there's the type of the object, which is a circle. Those two things we must distinguish. Now, we don't have that ordinarily. Let me just declare an integer. Integer I equals 99. Okay, the type of variable I is int. The type of what I stick into it has to be an int. If this were to be 99.5, it wouldn't matter. I'd still put 99 in I because it's an int. So it doesn't seem so meaningful here, does it? With a normal data declaration of a primitive type like int, float, bool, whatever. However, when we instantiate user-defined types, for example, in this case, a circle, and when I have a pointer to base, I all of a sudden enter a new realm where I have the type of the variable, shape star, and the type of the object, a circle. Now, because these two are different, this requires that the compiler implement a vtable, a virtual table, so that it can do virtual function lookup. Now, what do I mean by that? Well, what I've done here is I have a function called print area that accepts a pointer to shape. And what it does is, whoa, I don't want to do that. What am I doing here? Print area. Oh, and then I print the area. Okay, so I get the name and then I get the area. I'm sorry. And the important thing here that I want to point out is that this is a non-virtual function, but this one is a virtual function. When I have a pointer to base and I call a non-virtual function, that function call is dynamic, is actually bound to the type of the variable, which is shape. So when it looks for get name, it's going to start by looking in shape. It goes up here to shape, sees that get name is non-virtual, so it doesn't look any further, and it calls the get name right here. So I'm going to return circle right there. Now, when it gets to area, it says, okay, S is of type shape. So it goes up to the base class and looks at area. That's the function I'm calling, area. Area is a virtual function. So since it's a virtual function, and I'm not going to say that pun by virtue of the fact that it's virtual, although I'm dying to, excuse me, because it's a virtual function, the compiler looks at the type of the object Excuse me. Not the type of the variable. Now, what's the type of the object? The type of the object, we know it's a circle because we passed it in. How does the compiler know? It does a vtable lookup. And it has a pointer to the actual function that it should call. And what function is that? Well, the type of the object is a circle, so it comes down to circle, calls this function that's dynamically bound. That's what dynamic binding means. It means that I could have an if statement and I could call this function print area and I can pass any shape that I want. Circle, rectangle, square, on and on and on. And when I ask for the area, then dynamically the compiler will do a vtable lookup and say, oh, I got to call the area in this case circle, or if this were a rectangle, the area in rectangle. So let me go ahead and compile this and show you that I'm going to get pi r squared. So pi is 3.14, so that's about 50. Wait, we square 5, 25. 3 times 25 is 75 and change. So 78, I don't know. Let me compile it and run it. 78.5. Okay, so that's what we would expect. Now I could say this is a rectangle. Let me do that. So now I'm going to put rectangle. And for rectangle, I got to pass in something else. Okay, and I should get 30 this time. So watch, I'll get 30. Why will I get 30? Let me run it. There, I get 30. Why? Because this time I passed a rectangle in here. And when this function says, okay, we got s.getName, well, that's non-virtual. We use rectangle because that's what he passed in. So you see I get rectangle. Then he passes 5 and 6. So I'm going to call area. I come up to shape. I say what kind of a, and you know, even if this were a virtual function, not pure virtual, but virtual, I want you to know, let me just make it virtual. Okay, so in that case also, I will get the dot. Is it mad at me? Why is it mad at me? Oh, what did it do? Because I didn't what? Oh, it's mad. You know what? Let me do this. There I go, playing around. Why am I playing around? Let me show you that I get the same thing happening. Okay, so watch. I'll compile it. Now, control reaches end of non-void function. Area. Oh, this compiler. It's so picky. Let me just return something here now. Okay, so what do I have here? I have a virtual function. What I'm trying to show you is because it's a virtual function, I will still dynamically bind the call to area to the type of the object, not the type of the variable. So watch. If I can finally get this to compile, okay, I compile it, I run it, I still get 30. Because why? It's a virtual function now. It doesn't matter that it's pure virtual. By virtue of the fact that it has the word virtual in front of it, the function call will dynamically be dynamic. Oh boy, will be dynamically bound to the type of the object, not the type of the variable. Okay, it's early. So I create a rectangle. I pass that rectangle up to print area. It says get name. Okay, non-virtual. Get the name rectangle. Then it says get area. I want to find the area. It comes up here and says, well, it's a virtual function, so I got to look at the type of the object. I do a vtable lookup. The type of the object is rectangle. I compute area like this, and I get the right answer. So that's virtual. That's what virtual means. What I'm trying to show you, whether it's pure virtual or virtual, it's the same thing. Virtual is the key word that empowers this really polymorphism, frankly. This is a polymorphic reference here. That is, if I have a shape star S, S can take on the form of either any of the shapes in the inheritance hierarchy, circle, rectangle, any that I have. Okay, so there's one more thing I want to talk about here. So I'm going to go back to that vanilla example that I had before and show you that one. Okay, so let me bring it over here and show you this one. Now, what I want to point out to you is that I have base class A's. This is A and derived class B. This is from video part 1 on inheritance. And what I want to show you is that I have this virtual destructor here, and I don't even have a destructor here. So let me write a destructor. So a destructor, we put tilde B, and I'm just going to put std : C out, destructor in B. And I want to show you something interesting. Namely, that destructors in a base class should be virtual. Now, it doesn't mean it's not a big deal here, but I just want to show you what happens if it's not. Okay, so the destructor is virtual. So first of all, so let's come down to main. I'm kind of bouncing around here a little bit, but in main, I instantiate a B. I do a print, so that means I get the print in B. And then I delete X. So that means I have no leaks. So let me just do this. Let me go back to the top. Let me make it. Why is it mad at me? Oh, what is it saying? Error. It's an error. Line 33. 33 is an error. What? Why is there an error? Let me see. There's an error here. Am I in the right place? Well, you know, if it won't compile, just try again. Oh, did I delete something here? What did I do? All I did was A star X equals new B, X print, delete X. I can't understand what I'm doing wrong here. It says, let me start again. Okay, let me find this. Okay, line 33 expected as, I missed a curly brace somewhere. Where? Public A. What did I do? Let me go back all the way to what I had. Okay, there. I must have done something. Let me see if it'll compile now. Oh, okay. So I run it. And what happens? Oh, I wanted to put I put a destructor in here. Let me try putting a destructor again. Tilde B. You probably know what I did wrong, but let me try it again. Okay, so what do I want to say? Destructor in B. Think I can do it right? I must have forgotten that curly brace, huh? You know? Let me try it. It compiles, it runs. Okay, and I called the destructor in B. So let me get rid of this delete first. Okay? You know, it's risky me writing code, isn't it? So let me clear the screen, compile it, and run it, and show you Salad Kinnear. Now, first of all, I did a new, but I didn't do a delete. That means I've got a memory leak. Let me prove it to you. Okay, so if I run this, it says, okay, 16 bytes lost. Why? Because I newed it, but I didn't delete it. Now, that's the first thing. However, I have a virtual destructor right here, okay, in class A. And I have a destructor in B, which is actually virtual. Okay, so let me just try this. So let me run this. I'm going to compile it and run it, and notice the destructor in B is called, and if I run valgrind, you'll see no leaks. Now, if I do not make this this destructor virtual, what I want to point out to you, I won't have any leaks, but I could. Why? What happens here? When I say delete X, the compiler says, well, what's X? X is an A star. Okay, so let me go up to A and let me call the destructor. This is a non-virtual destructor, so it's only going to call this destructor and it won't call the destructor in the derived class. So let me show you that that's the case. Great. Look, I get a warning. Delete called on A that is abstract. A is an abstract class but has a non-virtual destructor. And if I execute it, you'll see I didn't call the destructor in the derived class. And so I even get a warning. Warnings are usually errors. In this case, it's not an error because B doesn't have any data attributes. But if I had a pointer in B and a destructor that deleted that pointer, it would not be called. Let me put the word virtual back here. Sorry, can I get it in there? There. Now I put the word virtual in there. I don't want to quit. I want to save it. I put that in there. Now I compile it, I run it, and I call the destructor in B. No warning this time because I made it virtual. So no big deal. All I'm saying is the way virtual functions work, it looks at the type of the variable. X is an A star, and it comes up here into A and says, okay, if the function is virtual, then I also want to use the one down here. And destructors are called bottom up, so it's going to call the destructor down here. And let me just show you they're called bottom up. So I'll put this up here, and I'll say this is virtual. And I'll make this be an A, and you know it's risky for me to write code. And I want to show you that we first call the destructor in B and then the destructor in A. Okay, so watch. I'll compile it. It actually compiles this time. I run it, calls a destructor in B first, the derived class, and then it comes back up and does the A. Why? Well, the object is of type, the X, the variable, is of type A. When I delete an A, I come up here into A and I say, okay, there's my destructor. I'm going to use it. Whoa, it's virtual. So I get down here first and I call the destructor in B. And I get whatever, and of course if there was something here I would delete it, and then I come back up and I call the destructor in A. Okay, so that's just kind of on my part an attempt to explain what the word virtual means and what it can do for you. We're going to have one more video in this series, and I'm going to talk more about polymorphism, which is really a powerful technique to use in object-oriented programming. Okay, happy programming. Brian Malloy, over and out.